One of the reasons for which calculus was developed is to answer questions in the sciences, primarily physics. But, as it turns out, because calculus is the study of things that change, the applications hit every field in the world. There's not a subject you can name that doesn't have at least some calculus-related development in it. And by the way, a student challenged me to that and said art history. And I said, I need you to look up the development of carbon dating and its use in art verification. And the eye is about that big, and lo and behold, you can tell the age of a painting using differential equations. You can tell the age of the paint, the canvas. Almost every piece of a painting can be dated appropriately this way. But I'm going to start with a motivating example. Let's consider a population of a group. Now, I don't care if you're studying bacteria in a dish, fish in a lake, deer in the forest, human beings on the continent of Australia, doesn't matter. The population changes over time. But last time I checked, birds, fish, deer, bacteria in a dish, whatever, new members of this population are being created and eliminated over time. So the change in this population is not constant. If I have a pond that has one fish, a year later, how many fish will I have?
A lot more.
If I only have one to begin with, either I have one or zero, right? Either the fish keeps living or it dies. But if I have multiple fish, some population, they might breed and I could end up with a lot more, right? But again, there could still be some death, there could be some change, but it depends on how many I start with, right? Aha! So the population is somehow dependent on, the change is dependent on the population. Now, this is the simplest possible model. Constant growth rates. This is primarily useful with the bacteria in the dish example. I think of a colony of bacteria. Over time, those bacteria divide and create more, and I end up with lots and lots and lots of bacteria in my dish. This is how culturing is done when you do medical examinations. They take a swab, they put it on a dish, they put it in the temperature-controlled environment, and they let it grow over time. And then they tell what sort of bacteria are in there. What I've written down is an equation relating the derivative to the original function. And that's my definition of a differential equation. What does this P of t look like? Well, let's go through the functions I know. P prime is a multiple of the original function. That leaves out every possible polynomial on the face of the world, right? Because when you take the derivative of a polynomial, the degree goes down. It leaves out logarithms, because when you take the derivative of a logarithm, you don't get another logarithm, you get 1 over x. It leaves out trig functions, because there's sine, there's cosine, there's tangent, secant squared. None of them match themselves exactly, or at least up to a multiple. What's a function that is exactly equal to its own derivative? E to the x. So if I can figure out how to account for that k there, I can use an exponential. Well, if I want my derivative to look like k e to the something, I could think about the chain rule. And I could say to myself, well, maybe that k comes from the chain rule. If the k comes from the chain rule, then it's the derivative of the inside. Well, that's where this question mark is. That would be the inside. So if k is the derivative, then the inside was? Say again? Well, but the derivative of k itself is 0. K is the derivative. What was the original function? Huh? Kx. The derivative of e to the kx is e to the kx times the derivative of the inside. There's my other k. That's exactly what I wanted. So a function that looks like this works. Hey, wait a minute. If this function works, so does any multiple of this function, right? I could add any constant you want in front of that, and I would still get a function that worked. So there's a function that satisfies my differential equation. Now I should put some limitations on these numbers c and k, just for a second. C could be any real number, and mathematically this would make sense. But if c is negative, then what does that tell me about my population over time? I'm sorry? Well, actually worse than that. If c is negative, or even if it's equal to 0, I don't actually have any people, do I? I have negative things. Do you know how to have negative bacteria? Negative deer in the forest? Negative human beings in a city? This is not I Am Legend. No, the people are still real. So that doesn't work. So I'm going to require c to be a positive number. And again, this is a population over time, right? So most of the time, I'm not concerned with negative t values. But I'm going to run the experiment on my dish of bacteria, right? I put the swab on the dish, I take the sample, I put it in the climate controlled room, whose name I've just forgotten. I wanted to say autoclave, but that kills everything, and I know that's wrong. Lab sciences were a long time ago, people. I put it in the growth position, and the medium starts growing. I really care from when the experiment started onward for positive t values. But if I'm looking at the population of a city over time, I might want to say, well, let's start at 1900 as my baseline year. Or let's start at 2000 as my baseline year, but the city might have been there since 1785. There might be value to a t being negative. We have to make sure that our model allows for both options. Most of the time we'll be concerned where t is positive. But if I set up a baseline like that, It could be related to some particular day, time, year, etc., or it could be when I started the experiment. But if I do that, then I know the value P of 0. What's that? The value of C e to the k0. Yeah? Okay, hang on a second. That's an exponential. But there's a C in front. So I get C e to the 0, and e to the 0 is 1, so that's C. So this could be my initial or starting population. It could be my baseline population. I don't know which to call it. That depends on the situation. In my bacteria example, it could be my starting population. In my city example, it could be the baseline population. That's based on the time I started. This model works for something I'm pretty sure most of you hold near and dear, money. You put money in the bank. The bank loans it out, charges the person they loan it to interest, and gives the interest to your account. Your savings account earns interest. Well, if you do nothing to the money that's in the bank, it grows just like this, depending on what K is. But then C is the amount you put in the bank, your initial deposit. Again, a starting value. Maddie, I said, what happens when C is 0? You gave me something about the population rising or falling. That turns out not to be based on C. That's based on K. Grab your calculators. Let's just use C equals 1 for the moment. I want you to graph e to the positive number times x, e to the negative number times x. I want you to use some numbers bigger than 1. I want you to use some big numbers, some small numbers, some numbers close to 1. Let's graph a bunch of things that look like this. See what we get. There's my graph for e to the x. K is 1, C is 1. Oop. Oh, I forgot I still had that Taylor polynomial in here. Let's get rid of that. There we go. There's e to the x. If I do e to the 1.02x, that's only a little bit bigger than e to the x, right? Very hard to tell those graphs apart, isn't it? There are technically two graphs there. It's very difficult to see. I'll change my y scale so it looks a little easier. There's the first one, e to the x. The 1.02, I saw it. There's just a little bit of difference right there. If I make this e to the 0.5x, what do I get? A slower growth. E to the 0.1x. Oh, way slower growth there, huh? As a matter of fact, the closer k gets to 0, the slower and slower this graph grows. The further we get from 0, the faster it grows. What happens when k is negative? e to the negative 0.5x.
Here itself.
So e to the x is growing, e to the minus is falling. Now, if I really was only concerned with time from when I started the experiment forward, there's a serious difference between those two. Yes? As a matter of fact, the same comment occurs. The further away from zero that negative number is, the steeper that graph, the more we fall. E to the negative 2x is going down really fast. But e to the negative 0.2x is going down very slowly, close to zero. And, Gesundheit, each and every one of those graphs, no matter what the value of k, they all have one point in common. They all have the point 0, 1 in common. If you put a c in front of that, it'll be 0c. But it'll still all go through that point. If we go back and look at the graphs we were just drawing, we see all four of them go through that exact same point there, 0, 1. This particular differential equation and the resulting solution is called an unrestricted growth or an unrestricted decay model. And it is therefore limited in some sense of realism. Because if you think about what happens when, say, k is 2, then I get e to the 2x, and that graph just shoots up to infinity. I'm growing bacteria in a dish. Am I going to get infinity bacteria? Doesn't make sense, does it? I have fish in a lake. I'm not going to get infinite fish, nor loaves. I'm not that kind of person, right? Loaves and fish. There's a problem here that's not realistic. And as we saw earlier, there's got to be some sort of minimum threshold too, right? If I only have one fish, spontaneous generation is not a thing. I don't suddenly get more fishes unless you happen to get a pregnant fish to start with. So there's some limitation on the way this model works that's not really applicable. It would be nice if I could take into account limitations of space, resources, competition, predatory behavior, prey behavior. All sorts of other things need to be taken into account like that. Well, if I add one more idea, let's say limitations on resources. If I add limitations on resources, come on, you worked yesterday. Let's say there's some upper limit to my group, some maximum. And if I have too much, they're going to compete with each other, and they're going to kill each other off somehow, and we're going to come down to that maximum. And if we keep growing, then we want to somehow have a theory that says, no, after a while, you start to slow down again. Well, then I can say, let's not only have this kind of growth when my population is small, but let's also multiply in some factor that when p gets closer and closer to m, as p is close to m, this fraction is close to 1, right? And that makes this multiplication thing very small. And that means my growth is multiplied by something small and thus slows down. The unrestricted growth model was popularized in the early 1800s. And as a response to this, a guy by the name of Verlust in 1840 introduced this model, which is called the logistic model, and places a little bit more of a restriction on our population. Think about the fish in the lake. At some point, the amount of space in the lake becomes an issue. The amount of food in the lake becomes an issue. And if all of those things become issues, then what we end up with is a very different picture. Page 587. Here are some pictures of an unrestricted growth model. And what happens over time? Nothing. We just blow up to infinity. Here is a picture of the kind of solution I get when I graph that Verlust logistic model. Notice that there are two lines. All of my solutions go away from zero, they grow, they start to grow faster, and then they start to slow down as we get closer and closer to m. And if you start above m, well, then this number is actually negative. So your growth becomes negative, and you end up falling. Now that means that there are two values of the population where there's no change at all. When is my population not changing? Okay, if I don't have any population to begin with, then this term is 0, and dB dt is multiplied by 0, therefore it's 0. What's my other option? Aha! So those two values, if we hit either one of them, our population is stuck. They're called equilibrium solutions. And they actually come in several flavors. In our graph, for the logistic equation, my axes being labeled P and T, somewhere up here is P equals M. And we see that our equations look like this. And we see that all of those graphs are going away from the line y equals 0, and they're going towards the line y equals m. So one description of these two different behaviors is to say that our line p equals 0 is unstable. If you're ever so slightly above or ever so slightly below, as time goes on, you go away from 0. But the line m is stable. As time goes on, you get closer to m, no matter where you start. So you could be able to say, just by looking at those pictures, that over time, this logistic model will settle down to a population close to n, whatever that upper threshold is. Questions? I promise we will actually do some examples, and I will show you how to graph these things without solving them, and then I'll show you how to solve them. On our Canvas page, there are two apps, an iOS version and a Google Play version for the app Slopes. Slopes allows me to draw equation. You can get it through the iOS store. Hard to see through the stupid light. There, Slopes. You can get it through the iOS store. You can get it through Google Play. You can put it directly on your MacBook. You don't have to opt a phone or a iPad. You can do it on your computer. I think it's helpful to have it in lots of different places. I have it on all three of my devices, my iPad, my phone, and my MacBook. It's also on my computer at home in the Google version. So the whole goal is that that app will draw this picture fairly easily. We'll use it later. These two examples are called first-order differential equations because they involve the first derivative. Shorthand, DE, differential equation. But there's no reason I only have to do first derivatives. Who's taking physics? Here or anywhere else? Okay. There's an experiment done almost every physics course on the face of the planet involving weight on the end of a spring. You measure the constant on the spring, you figure out how stretchy the spring is by putting the weight on there and hanging it, and then you pull down and you let it go and it bounces for a while, right? Well, the force exerted by the spring is due to Hooke's law. And Hooke discovered that if you take a spring and when you put the weight on it, it stretches, to a new place, we'll call that distance x. From equilibrium to stretched, we have a distortion, a displacement, x. Hooke discovered that the force exerted by the string is directly proportional to how much you stretch it. And it's in the opposite direction. When you stretch the spring, it wants to pull back in. When you squeeze the spring, it wants to push back out. That's what the minus sign here indicates. Hey, go the other way. But Newton tells me about force. What's Newton's second law? There are three of them. What's the middle one? Force equals mass times acceleration. But I remember last semester, we thought of acceleration as change in velocity, and velocity as change in position, change in displacement. Which means I can think of that A as a second derivative. I didn't write x double prime, I wrote it in the other notation, but that's okay. And now what I end up with when I combine these is a second order differential equation because it involves the second derivative. And that means I need a function whose second derivative is related to the original function. Now, I'm going to cheat one thing here. If I divide that m to the other side, I get the second derivative all alone, right? So I can write this equation like we wrote the first derivative equation. I can write the second derivative of x with respect to t is some number times x. And now I again ask the same question. Functions whose second derivative are multiples of the original function. Well, e to the x would still work, right? Problem is the minus sign. Not sure I like that as much. What other functions, when I take two derivatives, we get something related to the original? Before you actually think about what functions might work, what's the picture? You stretch the weight, you let it go, what happens? Well, what happens after that, Jack? It comes up, but then isotropic functions, like sines and cosines. Wait a minute, what's the second derivative of sine of x? And there's the minus I wanted. Now I just have to figure out how to deal with the km, sum of them. And that's why we call it simple harmonic motion. And it's related to the series. Sorry, couldn't resist. Now, I don't have to restrict myself to first derivative, second derivative, third derivative is equally important. Fourth derivative, fifth, it depends on the situation I'm working with. Modeling situations by differential equations is the difficult part. There are lots of chemistry examples, physics examples. We did this when we talked about acceleration. What's change in acceleration called? It was a long time ago, people. It's got several different names. Think about being in the car, stopped at a stoplight, and then you drop your foot to the floor when the light changes, what happens to your body?
The chair is backward.
Third derivative is called surge or lurch or jerk. Look at your feet. The change in acceleration. So I could write an acceleration differential equation and look at the change in the acceleration. Now, why do I care about changes in acceleration? Because changes in acceleration are related to stress and strain on material components. If I accelerate suddenly, things slide around inside my object. I have to strap stuff down carefully. I have to make sure it can physically withstand being accelerated like that. This is some of the problems we have with modern jet technology, modern rockets technology, and modern automotive technology. If you drop your foot and floor it, you can literally cause the engine to rip out of your car. A 1962 Dodge Dart GT, my father's car, gorgeous car, maroon with a white interior. You sit at the stoplight and rev the engine, and the car dips. Front passenger tire dips because the acceleration is causing it to spin and push on the motor mounts. The jerk and surge in that engine caused the whole car to turn. Go watch drag races, real ones, NHRA, National Hot Rod Association, and watch what happens to these crazy looking cars when they floor it. And I kid you not, the tires get thinner because of the centripetal acceleration. The engines twist on the mounts and have, in many cases, flown physically out of the car. The cars themselves have those giant spoilers. Why? To keep them from becoming airplanes. Same thing happens with boats in the water. Hydrofoils do exactly as soon as that nose lifts off the water, you hit a little bit of a wake, the boat starts to lift, the whole thing tumbles. Why? Because I went from a stable equilibrium to an unstable one. Exact same picture we were just looking at. I changed states. So I can have any kind of differential equation. Now, I don't have to just have one derivative. I could have something about y and y prime and y double prime all in the same differential equation. I can have 2 or 3 or 4 derivatives of the same thing related in different fashions. The order of my differential equation is the order of the highest derivative. If I have a third derivative in there, I have a third order differential equation. If I have a fifth derivative, I don't know why you would want to do something with a fifth derivative. You're wrong. But I can have any of these. So something like if I let y be a function of t rather than x, then I can write y prime equals ty. That's a first order differential equation. But this expression, y double prime equals 1 minus ty prime plus y, is a second order differential equation. I can have any order that the problem requires. And that's all. It's just going to depend on what do I need for that particular problem setting to understand what's going on well. Questions? I would like you to know that you have already mastered elementary differential equations. You've already done this. Because at several different points in time, I've asked you to solve things like y prime equals x cubed. What's y? Yeah.
It would be 1/4 of y and 4.
Hang on. Say that again.
It would be y 1/4 and y 4 plus the constant.
It's not y.
X and 4.
Right. Now notice we didn't just find one function. We found infinitely many functions that all satisfy my differential equation, didn't we? Even if I write this, y prime, then we can say, oh, well, then y must be 3/2 e to the 2x plus some constant. I found an entire family of functions that satisfy my differential equation. One of the problems we did way back when we were first learning to do antiderivatives, we talked about throwing a ball off of a cliff. It was one of the homework problems from last semester. 432 feet in the air, something like that. It's back in chapter 5. But we were only told about the acceleration. We integrated once to get the velocity, then we integrated again to get the position. I solved a second order differential equation. You know how to do that. It isn't until I throw y in on the other side that we start to have a problem. So that's my question, is how do I deal with those two pieces being in there together? But these were general. These were general antiderivatives. If I add a particular point, I want to solve this differential equation. This extra piece of information is either called an initial condition or a boundary condition. There's a very subtle difference between the two that's not relevant to this class, but I do discuss it in more detail in the general differential equations course. For now, I'll just call them initial conditions. But what do we do with that extra information? Exactly, I use it to solve for my unknown. And instead of getting a general solution, I can take the information from my initial condition and I can find a particular solution associated to that initial condition. So I plug in 0 for the x and 2 for the y value on the other side, and then I can figure out the value of c in this case. So here, e to the 0 is 1. This is 3/2. 1/2 0 squared is 0. So c is 1/2. And now what I have is a particular solution. And I'll use IC as an abbreviation for my initial condition. I'll actually go back and write that up here, IC. So this is the more general idea of a differential equation, but it's based off of what we already know how to do. And I will say that figuring out the rest of how this works takes two different approaches. The first of which is very heuristic and allows us to look at graphs and think about what is happening without actually doing the algebraic and calculus requirements to solve everything out. And there's something to be said for that. But there's also something to be said for doing the actual math behind it. So we're going to do both, but not until after Wednesday. So I will see you all then. I hope you have a wonderful rest of your day. I am posting the review sheet key and the home keys within the next 5 minutes. So you have them. If you have questions, come see me in office hours this afternoon. A wonderful rest of your day, everybody.